All right, 4.5.2. This first part is all focused on the light-dependent reaction. So when we're looking at the light-dependent reaction, we are looking at the top half of the chloroplast. We're looking at the thylakoid, okay? So when we're talking about that, the reactants, what does it need? It needs sun and water, okay? So we need sun and water. These are our reactants, and we are going to produce oxygen, NADPH, and ATP. This is just focused on this black section right here, okay? Now, describe how wavelength affects plants and how they absorb. These two bullets ultimately are the first part of the lab tomorrow, okay? I will talk about it right now, but the first part of tomorrow's lab deals 100% with wavelengths. Photosystem, all of the steps of the light-dependent reaction, and how ATP is a cyclic process. That's the part that's going to require some practice because you're going to have to keep remembering all the little details. Again, we are just on this kind of top part. So, for the electromagnetic spectrum, we have two different types of chlorophyll. We have chlorophyll A, we have chlorophyll B. Chlorophyll A is really our spring. It's our summer. It's when leaves are at their peak reflecting green. Okay, they reflect green. That's what we see. Chlorophyll B is like now. They're yellowish. So they're reflecting yellow or oranges. Plants have the ability to absorb short wavelengths and long wavelengths, okay? And ultimately, as you can kind of see, they're able to absorb blue and red. So blue and red gets absorbed, and what we see is what they reflect. They reflect green, which I recognize you're like, I don't get, like, why are we absorbing blue and red and all of a sudden we have green? That's really ultimately what tomorrow is. We're going to look at different types of lights through a light spectrometer, and that's going to show you how this kind of works, what you absorb and what you reflect. For us, the biggest thing that we have to remember, all of this is really ultimately in the thylakoid because the thylakoid contains chlorophyll. Chlorophyll is the key. Okay, the next bullet talks about the photosystems. The photosystems are like gigantic satellite antennas, okay? Ultimately, a satellite antenna's goal is to collect electromagnetic waves so your cell phones work. In this situation, our photosystems are gigantic satellite magnets for the sun. This is where we're like, we want to filter all of the sunlight into this specific spot to assist the process of photosynthesis. So like, I just think of the photosystems as like specialized antennas that are out there collecting the sun. And there's two of them. This light-dependent reaction is non-cyclic. It has a start, it has a finish. It is non-cyclic, meaning it does not cycle through like the Calvin cycle does, from start to finish, okay? With this, ultimately, everything starts with photosystem 2. That is where a lot of people get confused because they want to put 1 then 2. That is not how this works. It goes 2 then 1. As you can see in this picture, the thylakoid membrane, because we're in the thylakoid membrane is a phospholipid bilayer, so it has proteins embedded in it, and things can diffuse across its surface. So that's ultimately what we're talking about. The traveling of the little electrons, which I'll talk about in a minute, is the electron transport chain. So just so you kind of understand what I'm about to reference. Photosystem 2, it's almost simultaneously. As sunlight enters photosystem 2, water is entering into photosystem 2 at the same time. When water enters into photosystem 2 with sunlight, it breaks apart. So we now have hydrogen and oxygen. You just made oxygen. Oxygen now leaves. So ultimately, at the very beginning of the light-dependent reaction, oxygen is made. Because again, water comes in, sunlight comes in, it breaks them apart. Now, when water, which is hydrogen and oxygen, when they separate, electrons are released. These electrons enter the electron transport chain, and they really ultimately are traveling down the membrane. They then hit photosystem 1. Photosystem 1 is where they get re-energized. Okay, so more light enters, they get re-energized. They get so re-energized, they actually exit the membrane. They exit the thylakoid membrane. When they exit, NADP combines with H to make NADPH. Hydrogen is still left wandering until it finds the ATP synthase, travels through the synthase, which causes ADP to become ATP. Now, that's a lot of science. So let's Zangify it. Here's what you need to know for light dependent. Remember, everything we're talking about is light dependent. You've got Harry and Olivia. Harry and Olivia, they have been together a long time. High school sweethearts. Together forever. And Harry and Olivia, they've got a lot of kids. Harry provides for his family. He has a good job, okay? He works at Photosystem 2. It's a good gig. It's a gas station. He's high up on the food chain here. And Harry comes home from work one day, super energized because he just gets a big promotion. Harry's pumped. He comes home from work and he says, "Hello, family. I got a big promotion, so we're going to Disney World." And as any of you would be excited because your parents just literally came home and said, "We're going to Disney World. We're taking a week off at Gen Bio. Don't worry about that class. Disney World." Okay? So we're super excited. We are so excited, we rush into the car. We are literally in that car and we are buckled and we are waiting. Well, Harry didn't check with Olivia. It's a big no-no in Olivia's world. So, Olivia tells Harry, "I'm out. I don't want to go to Disney World." And Olivia, she splits. She heads off into the environment. She's gone. She's going to explore her options. Well, Harry, he's a good dad. So Harry holds true to his word, and he is road tripping with his kids to Disney. They travel along the membrane. "Are we there yet? I'm hungry. I have to pee." So he stops at Photosystem 1. At Photosystem 1, he lets the kids get out of the car and they re-energize. As you know, when you let children out of the car and you feed them candy and sugar, they're never getting back in that car. So Harry's children are running around and they're like, I'm not getting in that car. Peace out, Dad. And they leave. So the little electrons leave. Well, Harry is beside himself. He cannot let his children just run around unattended. But don't worry. Nancy is here. Nancy collects Harry's children. And Nancy says, "You know what, Harry, let's come to an agreement." And Nancy and Harry come to agreement that Nancy is going to watch the kids. An NADPH is formed. It's an agreement. Nancy is babysitting. newly single, free of his children, Harry, doesn't actually know what to do with himself. So he wanders. And he sees the light. And he knows. He's heard the rumors. It's sinful to go through ATP, sin phase. Harry knows he shouldn't, but the light from within draws his attention, and Harry goes through the ATP synthase. And he finds Addie. Addie's lonely and could use a little Harry. Could use a little recharging. So when Harry comes through that door, it's electric. It's energizing. It's electrifying. So much so that Harry asks Addie if he can come back. And Addie says, yes, please. So the art of Harry and Addie is actually a cycle. It's repetitive. Harry's road trip with his children is linear, non-cyclic. It has a start, it has a finish. But ATP cycles, you can never get enough. It's electric, and we need all the energy we can get because we're about to go into the Calvin cycle. And the Calvin cycle is meant for sinners. It's the dark side. So when we talk about the Calvin cycle, we are talking about the bottom half of photosynthesis, essentially the stroma. And within the stroma, it's dark. We get all of our energy from the top half. So we are now about to take NADPH and ATP, and we're going to use them to go on a roller coaster ride, because we were going to Disney World after all. So we should ride a ride. We need to be able to describe the roller coaster that is the Calvin cycle. We also need to be able to understand carbon fixation. That is 5.3. All right, so again, the Calvin cycle, we are still in a plant, just so everybody knows. Because earlier today, I was asked if plants can break up and get back together again and throw up, because I'm about to talk about how roller coasters make you throw up. No is the answer. These are very made up stories. So let's not take these for truth, okay? The science is true. The story out there. So ultimately our goal in the Calvin cycle, we need to use carbon dioxide because we haven't had an opportunity yet with carbon dioxide. So that's going to come in from the atmosphere, the environment. The goal is to produce sugar. Ultimately, if you look right here, it says, hey, we're producing carbohydrate. Well, carbohydrates are glucose. That's sugar. That's what we're producing. The thing I want to kind of add to our, like, hey, remember this. ATP is electrifying. It's our energy. But when we use ATP, it becomes ADP. So then we recharge it. The same is true with NADPH. It's a lot of work to babysit, so you better have energy. But as we all know, after we babysit, we've used up like all of our energy. We need a nap. so we can recharge. So just understand kind of that energy cycle. Here's the Calvin cycle. To start in the Calvin cycle, as with any good roller coaster, you need a car that you sit in and buckle yourself up. On the roller coaster known as the Calvin cycle, your car is RUBP. RUBP is kind of like the pre-starter point, so I kind of call this step 1. The step 1 is that carbon dioxide enters. So when you go on your roller coaster ride, you step up, you've waited for an hour in line, it is now your turn, you sit down in your cart and you buckle in so you don't die on this ride. Okay, step 1. Step 1 has a fancy name. It is called carbon fixation. Carbon fixation is, and genuinely, if you look at my notes, it says carbon dioxide enters. That's what's happening. So what is carbon fixation? Carbon dioxide is entering. Now, when carbon dioxide enters into carbon fixation, what we have to recognize is the whole art of the Calvin cycle is rearranging carbon molecules from like 2 to 3 to 6. So we're constantly rearranging the carbon molecules. So when CO2 enters in carbon fixation, we actually now have 2,3 carbon molecules. To go on said roller coaster, you have sat down, you have buckled up, and what is the first thing that happens on 90% of all roller coasters? You go up. And to go up, you need energy. So to get to step 2, you need energy. So ATP comes in, and we use it. Step 2, reduction. We've used ATP to get into step 2. We've used all of our ATP up. So to carry on with the roller coaster, we need more energy. Enter in NADPH. We're going to use NADPH, and it will become NAD positive throughout this process. But when we look at reduction, we are now reducing 2,3 carbon molecules into C6H12O6. 1 sugar molecule. Here's what I say happens on step 2 of a roller coaster ride. If you have a teeny tiny weak stomach, every single time that roller coaster goes whoop, 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 you are literally on the verge of blowing chunks everywhere. So, you reduce your stomach contents. You throw up your sugar. Because most of you have eaten carbs at this point in time at the carnival, whether it be cotton candy or corn dogs. You've eaten something you shouldn't, and now you're on a roller coaster, and it literally causes you to reduce your stomach contents. No, plants do not actually throw up. But here's the thing about you adrenaline junkies. It does not matter if you throw up after a roller coaster. You want to do it again. I don't understand. So, step 3, you need to get everything back to the beginning. So step 3 is the regeneration of RUBP. So step 3, we need to re-get the coaster cart, the thing we started with, back to the beginning. Well, how do we do anything? ATP comes in, regenerates or re-energizes us. We use ADP, but ta-da, RUBP makes it back to the beginning, where carbon dioxide will enter. And then it will be rearranged into 2,3 carbon molecules, where it will then be reduced into a glucose molecule that leaves the ride. We will then regenerate RUBP by adding in more ATP, and the cycle will continue over and over and over again. .3. Questions?